binary search tree. So as you all know, binary search tree, we should have smallest number on left side and biggest number on right side. So when we get our pre-order array, it would look like something like this: 8, 5, 1, 7, 10, 12. So the order is already in this array. So when we want to create our tree, the order would look like this. We have 8 and 5 and 1, 7, 10, 12. It's just according to so they already pre-order the number for us, and we want to return a tree node for the problem. So that is the problem itself. And now I want to share another screen. Wow, give me a sec. Can you see my graph? So.
Oh, okay, Doris, can you hear me?
Yes. Can you?
Can you pause a little bit, because some people have problems hear your voice.
I think everything. I can hear her clearly. No, I can hear her clearly.
I can hear her.
Clearly too. Yeah.
Oh, okay. So no problem.
Yeah. Okay.
Santina has a problem. Only.
Yeah. Okay. So maybe because of your internet.
Yeah.
Can she hear you guys?
Yes. Well, I don't know about that.
Oh, who knows?
Don't my message reply.
Okay, then maybe I keep going on for now. So
yeah, go ahead.
in my graph, so both of solutions came from other people. I didn't develop them, and I understand the first one better. Solution 1 on left side, and solution 2 is pretty advanced. I need to be honest with you. I try to graph it out, but I still cannot explain it very well. So we'll see. So maybe you guys can teach me something later. In the first solution, basically, here is our main function, and here is our insert function. And in our main function, we want to basically we create the new tree node using the first number in this pre-order array. So it would look like this. We want to create a tree node, a root with the first number in that array, and then we would get into a for loop here, and we would go through the pre-order array and then put in the number one by one into this tree node and return this tree node. This is our main function.
Can I ask a question?
Yeah, sure.
Well, why do you name it RES?
Result.
Oh, result.
Result.
Got it.
Yeah. Yeah, sorry.
I thought it's the rest of node.
I know sometimes it's response or something.
Yeah.
And that's why it's important to spell out your variables.
Because I see some other YouTube solution, they use RES too, and I was confused too. Yeah, now I got it. Everybody needs the result.
Yeah. Okay, good question. So before we do all of these things, we want to prevent some special case. So if our pre-order array length is 0, we want to return null. If our pre-order array length is 1, then we just simply return the first number tree node. Then if you don't have question, I'm gonna get into the fun part. This insert function. Okay, and it's here. So what we are doing in this insert function is we try to identify when we get a number, we want to identify is this number bigger than node value? If it's bigger, we want to put it on right side. If it's smaller, we want to put it on left side. Simply said it's like this.
Okay.
And I gonna try to explain it in graph. And you're gonna see this function again and again on my right side here. Okay,
So
I'm gonna
this is the way like when you write node insertion function, right? You just sort of write like this way.
Yeah.
Okay.
So in this for loop, I'm gonna loop through the pre-order array, and then I want to insert each number into this tree result.
Yeah.
Okay. I'll go to the brief part. So, shoot, what did I do? Oh, okay. So, at the beginning, we have our root. We create our tree node. Using our number 8. Number 8, our first number in our pre-order array. And then we bring this tree node to our second number in our array. And second number is 5 here. It's 5. Okay. So here we get into this function with number 5 and our 8 node. So now we have these two parameters. And when we get into this function, we would try to identify, hey, is our node an empty node? No, it's not empty node right now. So we just skip this part and come to next part. We want to see, okay, if it's not an empty node, then we want to compare the node value with our number. So our number is 5, so 5 here. And our node value is 8, so 8 here. So 5 is smaller than 8. So we want to insert this number on our left side because 5 is smaller than 8. It should go to left side here. So we would execute this function, this recursion function, and put in node left because we want to put something on left, and with our number 5 because that's the number we want to insert. And then
using recursion.
Yeah, it's recursion. We go into this function again with
Jen is an expert.
No, you are the expert.
You are the expert.
I learned on Friday from you, then was able to implement on Sunday. See who is expert because I learned from you. Your method is so effective.
This one?
Saturday, I'm talking about Ray. And Saturday, I'm like whole day. So your method is like 1 day instant growth.
Nice.
Yeah, I experienced that last time as well. That Sunday. Ray's solution is always the best. Okay, so here we come to our recursion. We come into our insert function again with our empty node. The reason it's empty is because you see our left side of 8 is empty. So here it's empty. We take node.left and it's empty with number 5. And this time we come into this recursion function. Our node is an empty node, so we create a new tree node and we return it. And we create a tree node with number 5. So it will look like this. We create 5 tree nodes and we return it back. So this tree node is attached at our node.left. So you can see it's here and it's at node.left. It's left side of our edge. And then we return this node, we return the whole thing and back to our for loop here. So now our result is this 8 and 5 tree nodes. And then we come into the second loop in this for loop with next number in our pre-order array. So far so good?
Yeah.
Okay.
Thanks for the explanation. Yeah.
No problem. I'm glad that you can understand. So we just finished the 8 and finished 5 and next number in array is 1. So now we come to 1. You can see that this solution is really not that efficient because we do everything again and again and again and we return everything. So now we have number 1 and we pass our node into this insert function again, and this node right now is this at 5, the thing we just finished. It's our current result, and we pass the number 1 into this function, and then we want to identify, okay, 1, we want to put it on left or right because 1 is smaller than x, so we go to left side, and now we have number 1. Do we want to put at left side or right side of 5? We want to put it at left side because it's smaller than 5. So that's why we go to node.left and then we go to node.left again. And then when we hit the end of the tree, we create a tree node with number 1. And we return tree node with number 1 back to left side of 5. And then after we have 5, 1, we return this 5, 1 back to the left side of 8. And then after we have all this 8, 5, 1, we return the whole thing again back to our for loop here. So now our result is 8, 5, 1. And then we want to go to next loop with number 7. Okay, that's pretty much like what we are going to do in the following steps to finish the whole tree node. Is everyone good with this solution? All good? Then let's get into another solution. And it's pretty hard. Even though I draw it out, I still have trouble understanding it. So be attention, Davian and Ray. We're gonna need your help.
I hope I can help. Let's see.
You got it. Here for you.
I'll try my best, but it's really. I know why it works, but I don't know how did he think of this solution. So this time we only have our main solution, but we have a sub-solution in here. This solution called create tree, and in this, when we get into our main function, we want to return this function create tree directly with the biggest number in JavaScript and an array. So this create tree function, we have 2 parameters. The first parameter is bound because it put the number into tree according to the bound. And I is a counter to keep track with which element we are currently on in our pre-order array. So if we at the beginning we will have 0 array, and then when we finish execute 0 element in pre-order, we will go to the 1, and we will go to 2, and we will go to 3 in pre-order. So we keep track with pre-order elements using this I array. So be attention, we are not keep track with this pre-order using no more primitive variable. We are using an array to keep track with that.
Wait, so I is your index of the pre-order?
Yeah, we could say that. Yeah, I is the index of the order.
Okay.
Thank you. Yeah, let's they can make it more understandable. Yeah. And then this is the function that we are going to see in our graph. So I'll just try to explain that in the graph. But yeah. What? So at node left in this function, we want to get into this recursion function with node.value as our bound, and we pass I again. Just I is the same thing all the way to the end. And our node.right, we want to get into this recursion function with our bound number and our I array. Okay. Then okay.
I'm still trying to understand what is bound exactly again.
So they are trying to use bound to identify we want to put it at left or put it at right.
Okay, gotcha.
Yeah. So, but also.
But what are the values of bound? Like, what are your examples like?
Yes.
Of bound.
At the beginning, we put in positive infinity. That's the biggest number.
Mm-hmm.
Yeah. And when we want to create left node, we create left node with node.value as our bound, and I as our index. And then when we create node.right, we create node with our bound, the original bound, and I. That's a pretty hard part for me as well. So after my graph, maybe you guys can understand it more than me.
just from what you mentioned, bound is your upper bound. So right has to be the upper bound. That's why it's positive. So whereas your left node has to end at the value of that node. You can't exceed that. So that's all I can gather for now.
Okay. So right now, let's keep that in mind, and we are about to get into the first recursion. So the first recursion, because our array, our index is 0, so we are on the first element in our array. So it's 8 here. And number 8, and so with bound, infinity bound, and index as 0, we want to first try to identify if this number in the array is it equal to our pre-order length.
Well, just to clarify, your I is not is an index, but it's an actual array element. It's the 0 element of an array, of an actual array. So your data type is actually an array, not a number, right? I. If correctly. Okay,
it's an array.
Yeah, all right.
It's an array. It's not a number.
Yeah.
So for our I0, we want to see if I0 the number at I0 is 0. Is it the same as pre-order length? No, it's not. And we want to also identify, is this pre-order number at I0? So I0 number is 0. So now we are trying to get the pre-order number, the first element in this pre-order array, and it's 8. So here is 8. And is it bigger than bound? No, our bound is infinitely positive right now. So for now, we will skip here, and we will go to next line in this code, and we're gonna create a new node with pre-order I0 plus plus. So the fun part of this is when we do I0 plus plus, we would actually return 0. So here we would return a 0. So now we want to get pre-order 0, so it's number 8. So we are creating a tree node with number 8. So it looks like this. But what happened with our I array is that our I array become 1. We have a 1 in our I array because we plus it. We change the value in I array. And then we go to next line. We create the node.left with our recursion function by passing in our node.value. Our node.value right now is 8. We just create it, and it's 8 here. And our I array is 1 in there. And then we go to the recursion function for this node.left. Yeah, here recursion function. And before I get into next picture, does anyone want to ask any questions, or we just keep going on?
Yeah, keep going.
Yeah.
Okay. So now we have our node 8, and we want to see what's on our left side of our node 8. So we go to here, and as you aware, now in our I array is 1. So we paste then here, our bound is 8. Our I array has an 1 in there. And now we know that we are trying to keep track with our input array with this I. So you can see that 1 here, index 1 is our value 5. So we are going to create a node 5 in this part. And then we are going to return this node 5 back into less recursion and put it at our node.left here. Okay, so what happened in this function is now we have our number 8 as our bound, and we have I array with element 1 in there. And then we come into the function, and the first line is still not true, so we skip that. And we come to next line, we create a new tree node. And now we know that our first number in I array is 1 here. We have 1 in our I array. So we would want to get pre-order 1. So our pre-order 1 is 5. So we are creating a tree node with number 5. So like this. Like this, we create a 5 as our tree node. And then now we want to identify, okay, what should be on our left side and what should be on our right side. So when we want to do that, we want to go to, when we do node that left, we want to see we'll go into the recursion function again, and with node.value 5, and with I2. Because here again, when we were trying to get the elements from our input array, we do I0 plus again. So at this step, our I increased by 1. So now we we have an element 2 in our I array. And we're gonna create our node.left by passing these 2 parameters into our create tree function. Okay, and we are going to we almost hit the end of our array, our tree node, so let's just keep going on. So now we are on the whole picture is, now we have node 8, and we know the left side should be 5, and then we are on the left side of 5, and we are on 1. So right now we come to here, and before we return anything, we wouldn't go to any right node. We are all on left node right now. Okay, so at here, when we want to create node 1, right now we come into this recursion function again with our bound 5, and with our element 2 in there. And we skip the first line again, and we create a new node using the third number in our pre-order array, so it's 1. We create a tree node with number 1. So it will look like this. We create a number 1 tree node, and then we will see what's node left and what's on node right. And then this time our node.value become 1 because it's 1, right? And our I have an element 3 in there. So when we go to the next level recursion from here, and if we hit the first line of the recursion function, now let's take a look at what happened here. So our value of I0 is 3, and our pre-order length is 6. It's not true. And we come to the other side of this if condition. Our pre-order number I0, so our I0 is 3. So our pre-order 3 is 7. So here we have a 7, and our bound is 1. So this time this condition is true. Our 7 is bigger than 1, so we return no. We hit the end of the tree, and we return node and back to here. So we know that the left side of our node 1 is no. And then we want to go to the right side of our node 1. Here. Here, we want to go to the right side. And we create 3 nodes using bound. And the bound is 5 right now. And we have I. We didn't touch I after here, so it's still, we still have element 3 in our I array because we didn't change it here and we didn't change it there. And so we still have 3 in our I array. And we come to here, we come into our recursion function again. And with bound 5 and with I array, 3 elements in our I array. Okay, so our I0 is 3 is not bigger than our pre-order length. Pre-order length is 6. And our pre-order I0, pre-order number 3 is 7. It's bigger than our bound. Our bound is 5. Pre-order I0 is 7, so we return a null. So we come back here, return a null. Now we can get the completed 3 null. We have left side as null and right side is null. So now we can return this node 1 to our last recursion. So we return 1, 3 node 1 back to here. So we know our node dot left here for our 5 should be 1 here. So our 5 dot left should be 1. And then we want to see what's on our right side of our 5 node. And we get into the recursion function again. And this time, if you remember, we didn't do any change on our I array. So our I array is still 3. We still have element 3 in our I array. And we have bound 8 because we didn't touch it in this level. It's still 8. So now we want to try to create node that right with bound 8 and I with an element 3 in there. So we are trying to create the right side of 5 nodes. Do I need to stop a little bit? Is everyone still alive?
Yeah. Well, you have that all computed all the iterations, right?
Yeah.
Oh, so then, yeah, then you okay. I thought you didn't have the solution, but you already have it done, so it's good.
It's so hard.
Yeah, well, because it's hard to keep track of the left. You have to maintain the bound until you complete the whole left side. So that's the trick they're doing here, or technique they're using.
The trick part for me is the array. I didn't. I tried so hard to understand what's going on with that array.
Right. Yep. Yeah, they're incrementing through the elements just for one side of the tree at a time. So they're handling it one at a time.
Yeah, one at a time. So the whole picture looks like this. So we create a node 8 and create node 5 and create node 1, and then this is empty and empty, and we return this at left side of both. This is both sides of our node 1, and the left side of 5 is 1 and right side is here. It's 7, and we have no empty and empty on both sides of 7. So we return node 7 back to 5. So now our 5 node would look like this. We have 1 and 7 on left side and right side for 5. And then we return the whole 5 things back to our node 8. And it's on left side of our node 8. So we insert this thing on left side of X. Yeah. And then for our right side, and after we finish everything on right side, insert it to X. Okay.
Yeah.
Can anyone?
That was very clever. That's a very clever implementation.
Yeah. That's amazing. It's amazing for me because I don't know who is so genius think of for this solution. But does anyone can tell me what's the time complexity and the best complexity for both of solutions?
Yeah, I guess we can. Yeah, we could give it a try. Go back to solution 1, or
is this a legal question or just general? How you?
She was bored one day.
Huh?
She was just bored. She just had time to kill and decided to make this graph.
You know, that would take me the whole day just to do that, to write that up.
I was so confused until she zoomed out, and then I was like, "Oh, it all makes sense now."
I was trying to help myself, but I'm glad that I can help some other people now.
I'm curious. Have you tried running this through Python Tutor? It maintains objects and arrays and elements and steps you through it. So that's why I don't like drawing these out. I just go through there and watch it.
I tried that once, but I didn't really understand what is going on there. Should I? Do you want me to put this into Python Tutor?
Yeah. Throw it in.
I would love to see this.
Track it. Select JavaScript in the middle.
Can I use that for pointer system so I don't have to manually point anymore?
Yeah, you definitely need this.
Davian, why you don't come early?
I didn't know it existed.
So much hard work, huh?
The hard work made you learn. Now you know binary tree.
Yeah.
Yeah, you went
the
straight
binary search tree.
Yeah, you went from arrays to doing recursion with binary search trees in no time. You jumped a lot of steps.
That's a vast difference between the two.
Yeah.
Oh my God, this one really. My God, I love this website.
Yeah, I use this a lot for
I need to get a solution first. That is the problem, right? If you don't have solution, you will not run the start.
Yes. Well,
yeah.
You don't. Yeah. You step through it and watch it.
I was trying to walk through the point system so I can get the solution, but this one is you got solution first, then visualize.
Yeah, that's all I got.
Yeah, because you have to call it and you have to input numbers. You have to give it number. You have to give it a tree, the array, right?
Yeah.
You have to call it with the array.
I don't have solution. This one, this website.
Yeah, you got to pass that.
So I still need the Davian.
Yeah, I use this site all the time.
This is news to me. I'm like, where do these people find these websites that do all these visualizations
Actually,
and step-throughs?
PWP course, they showed us, Kazi showed us this.
Oh, I haven't gone through it yet.
Has a lot of shortcuts.
But I've learned it from other sites too, from, I don't remember where, but.
And it's for JavaScript too, right?
Yes, Java. And I forgot what the other two options were. Was it Java or something else? Or C or C Sharp? I don't remember.
Probably one of those.
So you can't do ES6 stuff. You can't do file network calls.
Oh,
wow.
Look, you have array yellow stuff. Look.
Well, you have a reference or a pre-order. Do you have to define?
Pre-order is not
define with
defined.
a let or constant first. Pre-order let.
Sorry,
Yeah,
what?
it's not defined.
One.
You just have pre-order equals, but
Say let first, let or constant. It doesn't matter. Pre-order.
Yeah.
I mean, declare it first.
So this
How did I do that?
This site will draw a tree too. Like you put a.
Well, it'll show you the objects. It keeps track of all the objects and variables, and you can console log. It'll have another section.
I put a prop, then it shows the tree. Then I don't have to draw anymore.
What is this? Far left.
Tree node is not defined.
Yeah, because you need to. That was the problem when I had like practicing. You have to implement. You have to show. Well, you have implemented a tree. Yeah, you need a tree, so you have to show your other dependencies. Well, what is tree? You need to show your tree node implementation. It's like 3 lines or 4 lines of code, right? It should be like a value index.
Yeah, like your tree definition, whatever.
Yeah, the dot left, and the dot right.
And
Otherwise, it doesn't know what
and the value or whatever it is.
Because I was trying to do this the other day, and I was like, oh, I got to implement my freaking binary tree now first before I can even run it in here. You have to give it an implementation.
Yeah, that thing.
Yeah.
So it's more like evaluate your solution is right or not right?
Well, I mean, it's more to walk through, step through each step of your code that you can.
But what if you don't have solution?
Well, I mean, it's just
it's going to be a short walk. Very few steps will be taken.
It's the same thing as running code in your debugger in your console.
Variable, then variable print out.
Nice.
Yeah. I mean, I've posted some solutions on like people's I don't know, threads of like algorithms or whatever it is that they were doing, and I posted solutions using this.
Yeah, next time you're gonna teach us how to use that system for every question.
This is amazing.
Well, it's not always applicable for, like I said, it won't do like a network calls.
No.
I never know this existed. It's a whole new world.
No.
I mentioned this last week in Doris's call.
Oh.
Yeah, he did.
It feels like forever ago.
What? It was 8 days ago.
Like no one can think that far back.
Yeah, I know.
That is our successful coach Joe. Finally joined.
Yeah, that's what I said. Join. I want to take the class from you.
Yeah. Did a shout out for you, Jennifer, during that call.
No, turn on your camera.
Oh, Joe's here.
Yeah, Joe.
Hey, Joe.
Show yourself.
Yeah, don't hide.
Like Nas or Kanye or Sunny.
Yeah.
On the camera.
You know which question are we gonna working on?
I will stop sharing for now.
Oh my goodness, I just need one scroll of like all of these steps.
Yeah, it's cool, right?
Yeah.
It's pretty cool. And thanks for teaching me how to use that.
Yeah, no worries. Yeah, the only thing is, like I said, like you had to show your dependencies, like it was a tree. So I was trying to do a problem with a binary tree. And I was like, oh, I got to implement my own binary tree with an add and insert. I'm like, oh, I got to implement all this stuff from scratch. So I was like, forget about it.
So today I have solution. Can I use my solution to use this website too?
Yeah, you should. Yeah.
Okay. So what are we gonna do now?
I don't know your solution.
And that's it for this call. No.
How many solutions do you have? I only have recursive solution.
That's very good.
Do you have iterative solutions? Saving?
Again, just to make sure we're doing the right problem, this was the... Wait, I already forgot the name.
That one is called the branch
sum.
Yeah, the branch sum. Yeah, it's recursive. Like, I could not conceive of a way to do it iteratively. If there is one, I would love to see it, because the second I saw it, I was like, there's no way. Not for me.
Okay, so maybe I can just walk through the system very quick.
Yeah.
Or anybody wanna walk the system? Alright, I'm not gonna show my screen.
Now you're gonna go to, what is it, Python Mentor?
Python tutor.
Python tutor.
Python
Yeah.
tutor.
Okay, so anybody know the question? We
I
have
do, but repeat. You should
Jordan
repeat it.
Jordan gonna read the question, but he's not there.
Oh yeah.
Okay, hold on. Okay, so David gonna read the question. Oh, great. Oh,
Okay.
do
I can read it. Whatever. Sure.
Okay,
Branch
sure,
sums.
please. Yeah.
All right. Branch sums. Write a function that takes in a binary tree and returns a list of branch sums ordered from leftmost branch sums to the rightmost branch sums. A branch sum is the sum of all values in a binary tree branch. A binary tree branch is a path of nodes in a tree that starts at the root node and ends at any leaf node. So leaf node is at the bottom, which will have no child nodes. Each binary tree node has an integer value, so no floats and whatnot, and a left child and a right child node. Children nodes can either be binary tree nodes themselves or none or null. So yeah, and then you see the input. And
Yeah, input is this tree in the picture here, and the output is this one. Does anybody do not understand the prompt?
Yeah, so the output. So
everybody
yeah, so one sample thing is like if you take the leftmost branch, right?
Uh-huh.
1, 2, 4, 8. You take the sum of it. 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. So
Oh, I got it. I have that one.
Yeah.
Hold on. Let me find that picture.
I mean, yeah. Okay.
This picture
Whoa,
looks
Wow. Look at that.
Nice.
That's what we're talking about.
Yeah, so I don't have to type anymore. So how we gonna?
Well prepared.
Yeah. So how we gonna? Okay, do you guys want me show that one? We don't need to show the sample input, right?
Yeah, that's yeah, exactly. You can just show one.
Okay, let me do. Okay, so we're just gonna read the question, then according to that, walk through this traverse system, right? Or we're gonna write pseudocode according to this graph. What should we do, David?
So to
Okay.
wait.
Yeah, I don't know how to start Illustrator.
Are we illustrating? Are we
draw?
coding? Are we? What are we doing?
Are you trying to draw through?
No, I try to make people understand what problem we're gonna solve. So the sample input is this bigger binary tree, you know, this bigger binary tree, and the output is this array in the bottom, which is 15, 16, 18, 10, 11. And so it says a function takes in a binary tree, which is that colorful node, returns a list of branch sums ordered from left branch to right branch. So I hold on, I need to get my brush, green brush.
Oh.
Okay.
Oh, you use the same one Tata uses?
Yep.
Yeah.
Nice. How much does it cost? $3 or $10?
5 maybe? 4?
Three.
Something like that.
I spend a lot of time googling free options because I'm too cheap
Yes,
to pay
green
for.
one is better. Okay. Yes. Okay. So binary tree returns a branch sum. Do you know what is branch sum? So branch sum is like, for example, a branch. You know the tree, like for example, here we have a pink branch, and we can have the green branch and the purple branch. So it's like a branch is like a node linked together, then become a branch. Then we need to calculate the sum of the branch sum. Okay, so this tree returns a list of branch sum ordered from left branch sums to right branch sum. So I know does anybody know what is a binary tree? Okay, since we already talked about that on Friday, but I can repeat very quickly. So binary tree is a tree which has two children, right? Ren? It must have two children, right?
No. Has at most 2 children.
Okay, has at most two children. So which is 2 and 3. Then okay, so we have the left branch and the right branch. So you guys can see I already highlighted the left branch is the one in navy color. Right branch is the one in black color with no arrow side. So you got it. How can I see this? I don't want to use that one. Okay, so just like this, left and the right. You know, navy is left, black is right. Okay, so a branch sum is the sum of all values in a binary tree branch. A binary tree branch is a path of nodes in a tree that starts at the root node. So root node is the pink one, is the root node according to the definition from textbook. So, so we start from here, the pink one. And ends at any leaf node. So leaf node is the one in green because leaf is green color. So I just
Leaf node just means it has no children.
yeah, it has no children. So like 8, left no children, right has no children. It's like a pretty lonely leaf. It's not a tree, you know, like a Christmas leaf. Sad. So all the bottom one has no children, so it's green and it's leaf. They cannot form a tree because they don't have children. Okay, so each binary tree node has an integer value. This is obviously, you can see the graph, each binary tree node, so each dot is a binary tree node, has an integer value, which is a number like 1, 2, 4, 8. Everything has an integer value in the middle of the dot. Okay, a left child node and a right child node. So each binary tree node, like the 2, has left child 4, right child 5. 4 has left child 8, right child 9. Got it? So what children nodes can be either binary nodes themselves or none. So none is like the said leaf node, like 8, you know, like 8, all those green, which it's just the node themselves, and their children is like none, which is a leaf.
Yeah, like you said, so a binary tree means that each node can have at most 2. So it could have 0, 1, or 2 nodes. And the leaf nodes have 0. But, you know, other nodes could have just 1, you know, or 2.
Also, according to kind of like a traversal principle, when we sort of like go steps of search, when we reach the leaf node, so it's pretty sad and lonely, we just go back, you know, like the arrow. So that is how it traverses. So it's easier to remember. When we see leaf node, pretty sad, lonely, go back, you know, then go to the children.
Go back to its mama or papa.
Yeah, go back to parents. Okay. So that is how it is. Okay, so the question, the sample output is we wanna get 15, 16, 18, 10, 11. Does anybody know how to get 15, 16, 18, 10, 11? And this is the each number in this array, each number called the branch sums. So that is our goal. Our goal is to solve this problem, to find all the branch sums and put in an array and return the list of branch sums. So I hope everybody understands this question pretty well. Does anybody do not understand these questions? Okay, I guess nobody do not understand. So how I just gonna walk through how we get. Can you guys see? Okay, how we get the 15 rate. Okay, never mind. I just talk. So first we.
Oh, leftmost pass. Sorry, I was on mute.
Yeah. So we need. So the approach is 3 steps. So first one, we need to init a counter variable. So it like we name it current sum. So like when you do array, you always have like a cumulative variable. It like works as like a counter, right? So we just assign as start at 0. Then we're gonna create another variable called new current sum. So the new current sum, which is current sum, the counter variable, add each node value, which means the integer inside the node. Then we got the new current sum. So we're gonna keep on updating the value of new current sum. Then we got a branch sum, means we just add all the new current sum, become a branch sum. Then we push or append all the branch sums in the empty array. So that is the approach to solve this problem. So I can give a quick of the question. So like not question, like the problem walkthrough. So our current sum init as a 0 start. Maybe I should write pseudocode, right? Or I just work this one. Okay, so according to the formula on the right, new current sum is equal current sum plus no sum. So the new current sum here is the navy one, which is equal to red plus black become navy. Okay, so that is 1. Our new current sum is 1 now. Okay, so we're gonna keep on traversing to 4. What is our new current sum now?
3. Am I right?
Why?
Because it's blue. Because 1 and 2 are
Yeah, because new current sum is navy.
Yeah, it's blue.
Okay. Yeah, so okay, so we're gonna traverse to the next node. What is our current sum now?
7.
Current sum.
Oh, right. 3.
But because our previous new current sum is 3, but when we go to next node, the new current sum become the current sum, right?
Yeah.
The red become current sum. Then add the node dot value. Node dot value is 4. Then we get the new current sum updated. Now the new current sum is 7.
Yeah.
Okay. Then we're gonna calculate the, for example, one branch we got. We're gonna calculate the sum of this branch, which is 7 add 8. Because 8 do not have children anymore, so we just add that one because that one is node dot value. So our branch sum is 15. Then we put in the empty array. Then we're gonna traverse back according to the depth of search method. So we go this way. So we go this way. We go parent first. Ray, do you wanna talk about traverse order?
Where are we? Sorry.
Because you are good at traverse order.
Which traverse order are you doing?
So right now, okay, so first branch we from node just go all the way, called the depth first search, right?
Oh,
we got one branch.
Doing? Okay.
We got one branch, the pink branch. Follow the arrow direction.
Right.
So after we reach the third leaf node, what we gonna do?
I didn't see your code, but I assume you're following. Is it depth first search is it pre-order or is it in pre-order is considered depth first search? If it's
I believe
pre-order,
we're
it would
doing
be
depth
the
first search. Yes.
yeah. I don't remember if it did follow the pre-order because pre-order would be the root, the node, and then the left, and then the right, and that's the pattern. The current node, left, right, or parent node, whatever you want to call it.
Yeah.
So
Yeah.
eight, and there's no left, right, so it goes back up to 4. No left. Well, left we already did. The right is 9. Yeah, so that wouldn't. What the hell are we doing? 8, 9.
No, that's right. That's what we're doing.
Yeah.
So
what are we summing up? We're only getting the pink, right?
Huh?
We're only. What are you doing? The first branch only?
The first branch is pink. Then
Yeah.
we reach the third leaf node. Then the branch is finished. We got a branch now.
Yeah. Okay.
Yeah. Then we're gonna start the second branch.
Oh, okay. I see.
So we go back the parent node, and the parent has child. We go here.
Yeah.
Then see if this dude has child or not. Left no child, right no child. Go back. Then go back to parent.
Yeah.
So when we reach the leaf node, the branch is over.
Right.
Forms a branch. Yeah. Then this one go back to parent. 4. Then this we already kind of like traverse the children for that parent, right? So that parent gonna go the grandparent too.
Yeah, exactly.
Grandparent gonna see his child, which is 5. Then 5 gonna see if he has the kid or not. Then see here has 1. Then 10 do not have children. So we go back to parent. Then parent go grandparent. Grandparent to go the root. Grandparent.
Yeah.
Then that one is here. Then look at child and then no kids. Go back to parent. Parent see no kids. So finish.
Yeah.
So each leaf node is end of one branch. So we have how many branches total here?
5.
Yeah, so like a pink one, the green one, the black one, the red one, then the purple one. 1, 2, 3, 4, 5. Yes. And since we use the recursive method, so we just use my color system to get the number for each node. Then when we have that, then we summarize. Do I need to explain that one, or you guys already understand?
We are good.
Okay.
Elva and Joe, do you guys understand?
Yeah.
Nice.
Say nothing if you don't understand.
Okay, maybe Davian walk through because you explain better.
Do I?
You explain how get 16, 18, 10, and 11. Because I already talk 15 already.
I did one. You do all
so
the
you're gonna
others.
do the pointer system. You know which rule?
Okay. For those of who are gonna watch the recording later, you are gonna get all the cool screen brushes. So, but for other, if you're not, it's okay. So, basically, we're at 15 now. That's where you left off.
Yeah, 15 right here.
So you're at 15. We've reached essentially our base case, which is 8 has no children, no left or right, so we're going to return out of this function. And because we return out of this function, we then move up the stack to our previous node, which is 4. Now that we're at 4, now we're back in the stack that has 4 as our node value. In the order of traversing the branch tree, we start with the node, we go with the root node, with parent node, whichever it is, then we go left, then we go right. So now that we're at 4, which is our parent most node currently, I don't have a word for that, and we've already searched for the left, the next step is to again search to the right. So now we check our node's right value, we see that it has a value. So
yes, has a value.
Yes. We see this node has a value of 9. So we call our recursive function again and pass in all of our data that 4 currently has into this function. And passing in, and now we make 9 our current value, our current node.
Okay, how did we get to 7?
We don't know. No. How do we get to?
Oh, I just explained.
Yeah, you did. Oh, right. I'm like, okay. So we got. So
the formula is in the purple cheat sheet.
There's a lot going on here. Okay, like give me some slack. I didn't make the chart like you. Okay, it's very involved. All right, it's complex, like many people's emotions. So we got to 3. I'm not about to re-explain. Okay, we got to 3.
We get to 7. I know 16 is 7 plus 9 is 16. How we reach the 7 value?
Because it's 4 plus 3. Boom! I could do simple answers that don't answer any questions too. So. So.
How do we get 4?
We got 3 because each recursive.
How do we get 4?
How did we get 4? Because 4 is the current value of this node. And we're adding the value of this current node to all of its previous ancestors. You know, it just gets reincarnated each passing of the tree.
How do we get 3? Don't tell me it's red.
Well, you're doing a running sum total.
It's a running
you're
sum.
Starting from the root.
So
you're starting from 1 and you're accumulating. So you have your accumulator
so,
from the root. And the nodes that you're visiting, you're keeping a running total.
So we got our parent most node, which is 1. We're going a level deeper in the stack. Now we're at 2. And we've added the sums of 1 and 2 and passed that down to which child 4. Now 4 has all of the genes, or the DNA, whatever you want to call it. It's inherited all of the values of 1 and 2. And now it's going to pass that to its child, which is 9, and now 9 is going to inherit all of the previous values of the parents that came before it, and that's how we get the sum 16. But it died there, so we just return it back up, and we just travel back up the tree.
Yeah. Okay. Does anybody wanna continue about 18, 10, 11, or it's enough? Eric, do you want to explain 18 with my color system?
She would love to.
Yes, please. Eric.
All right, Alva, you can do this.
Yeah.
You got
Let's
this.
do it. So that means my teaching method is pretty good. Everybody understand.
Okay.
Yeah.
Should I
We can start from root, or we can start from leaf node. Which one do you like?
Oh my god, I don't know.
Start from the root. Start from the root.
Start from the root, okay.
Okay.
So, from the root we have a current sum, and we add to the current value to the current sum.
Yeah.
And we pass down to 2.
Mm-hmm.
And from 2, we add the current value 2 to the current sum, and we
Yeah.
get a 3.
Mm-hmm.
And we pass the sum to the next level, which is, should I go 4 or 5? 5, right?
Yeah.
5.
Okay, then I go to 5. Then now we have a current sum of 3 plus the current value is 8. Then we pass down to the next level, and now we have an 8 plus current value 10. That
Yeah.
total sum of 18. But if we try to go down one more level, there's nothing to go, so we return back
Yes.
up.
Right. That's it. Okay, Doris gonna talk about 10. Then we done.
Okay. So, I think from root is easier.
Oh,
After we hit the node 10, so there's nothing after that, and we just return all the way back to the root, and we want to go to right side of the root. So our current sum is 0, and we plus 1, so we go to next node. It's the current value is 3 plus the current sum was 1. 1 plus 3 is 4, and we go to next node. It's the value is 6, and our current sum was 4, so we plus 1 and 4 and 6, so we got 10 at the end. There's nothing after 6, so
yeah.
we put 10 into our array, then we return.
10. Yeah. I think everybody got it, right? Okay. Okay, so we're gonna work on the pseudocode and the real code now?
Yeah, I thought you already had the code there. I'm like, what? Because I'm like, just
I
plug
have
it in.
code. I thought I was gonna, are we gonna build you driver and the navigator?
Sure, whatever.
Well,
And passengers.
No. Who?
I can be a driver. I did deliver.
Maybe Ray be navigator. I think everybody got the solution, right? Or no?
I got it.
Well,
We
Jen,
don't
you already
know.
have your solution, so you can navigate your solution with Doris driving.
Okay, I navigate the solution then.
Yeah, Doris will drive.
I can drive. Or Elva. Elva, do you want to drive?
Can you drive? Can you really drive?
Yeah.
I wanted to drive, but I'm not connected to the link.
Oh, the line.
Oh,
okay.
drop the
Already-
link. Oh no.
I give you the.
She couldn't connect?
I'm not sure like what's going on, but I'm not able to connect. I'm guessing.
You may have to manually like copy and paste the link into the live share plugin or extension. Sometimes that happens.
So maybe one person drive parent function, another person drive child function, whatever. Okay.
Yeah.
So they just gonna take a nap, right?
Oh, exactly.
Take a
Absolutely.
nap in the back.
100%.
Okay, so are we gonna do it now? So first step, we gonna okay, we already have this created, right? Ren, can you explain what is this from line 28 to 34?
Oh, that's just your the constructor class for binary tree. That's the representation of all those nodes. So the constructor takes a initial value, an integer value, and assigns it to this sub value, and then it initializes the left and right filter nodes to empty or null. So you just instantiate it with that root value.
Okay. Okay, so everybody understand that. Okay, don't need to look that one. Okay, first we're gonna create a result array to store our current sum. So create a result equal empty array. Yeah.
Do you want me to?
You wanna answer the one code, right? Doesn't matter.
Who's coding
sure.
now?
Sorry?
Who's
It's me.
Oh, okay.
He's driving.
I navigate. You guys help me navigate.
No, I'm just
You
in the
know.
back eating food, like just talking at the drive-through window. Like I'm good back here.
Okay, then next step is we're gonna create a helper function named the calculator branch sum. That need to be together. The calculator branch sum. Because it's a yeah, you know the the helper function. Yeah. Okay. Yeah. So that helper function will take in 3 parameters. One is the root, which is provided here. Second parameter is our current sum start value 0. And another parameter will be the sample result that we are trying to return. Yeah. So calculate branch sums. Yeah. Okay. Root 0 result array result. Yeah, because you named the result. Yeah.
Am I right?
No, 0. Because we're gonna init as 0 first. And the result. Yeah. Then we're gonna return. Yeah, so inside the pink curly braces, we're gonna return result array. Yeah, return result array.
Did you say return result array? That's
Yeah.
it?
Yeah. How come here has this? I don't know, but doesn't really matter. Okay, so we're gonna create a no. Oh, yeah, because you are using what? Arrow function? Okay, fine. Okay, so we're gonna create a helper function outside the parent function. Outside.
Like
here? Yeah. So that's line 42 is Ray taught me that is recursion call itself, right? Call the helper function itself. You taught me on Friday. And the return inside the parent function, not a child function. Oh, not.
That reside within the same function.
Yeah.
Within the code block, the function block.
Yeah.
Or declaration, function declaration.
Yeah. Okay, so we're gonna create our helper function outside the parent function. We're gonna call it function calculator branch sums.
Wait. So we are calling function here. We are not defining.
No, we're gonna. Yeah. We're gonna create that one outside this is our helper function. This line we call our helper function, right? So we're gonna create a helper function in line.
Does she have to define it at 42 as definition, DEF, before calculator branch?
I use function, I don't know.
Oh, yeah, function. Yeah. Sorry, I'm thinking Python. Yeah, function.
Yeah. Maybe you just use that one, then change it to ES6, calculate some, it takes 3 parameters node. I think one is node. Second parameter current sum, which is the red one. Then result array.
Okay.
Yeah. Yeah. Then inside this helper function, first I learned from Davian. We're gonna check edge case, make sure there is no empty tree or leaf node. If it's yes, we just gonna return directly because it's just empty Christmas tree. Just return. So I learned that one.
Were you looking at my icons in my reply the other day?
Yes. So node equals none. Yeah. Yeah, you can do that one too. But they can get the node equals none. Yeah. And return. Right. Then after.
If you want to be concise, you just say not node.
Yeah, but just use that one because they can use that one.
I just used that one because I thought everybody might get confused if I used not.
Yeah. Do we need a 3 or 2?
Yeah, it's just strict equality, coercion. You check for coercion, but yeah it's fine.
Don't look at me. I'm using not when you guys aren't looking. I just do this because it reads better.
Two equal, right?
That would equate to the same thing. Yes.
Yeah.
Okay. So we are not using Davian. We change now. Okay, fine.
This is how I submit my code. It's using the not. It's using the bang, whatever we're calling it.
Right. Ever he get the node equals none on Friday, right? You saw it. You witnessed.
It's all recorded.
It's all recorded. Don't snitch. It's on tape. Okay. Call me a 4K.
Okay. We won't talk joke anymore. Okay, so after that we're gonna create a new variable called current. New current sum. New current sum, which is let me see. That graph is the navy color one. We need that variable to keep a track. And that one is equals current sum, the red plus the black. So current sum plus node dot value. Okay, then I don't know why. Then we just got the new current sum. Then we just push the new current sum into the empty array result. Yeah, push new current sum. Okay. So after we did that one, then we're gonna do the advanced called the recursive function. So you
just fix your node dot value at the end of line 53. NODE. Node dot value.
Oh, sorry. Yeah. Great. Okay, so after line 54, can you write a pseudocode called the recursive function? Yeah. Then we're gonna call a left node and a right node. So we're gonna put a calculate branch sum node dot left. Yeah. Node dot left. Then new current sum.
New current sum.
Yeah, and the result.
I don't know how to spell. Current sum.
Yeah, result. Yeah, semicolon. Then we're gonna call the right. Yeah, then new current sum right. So basically the recursion we call the left branch the navy one. Then we call the right branch the black one. Okay, then we return the calculator branch sum in the parent function. Then we done. That is what I learned from Ray and Davian. Oh no. Let me see if I got right. Yeah, I think so. Should we run that?
Wait a second. I don't think so. We are not defining the function here, so we don't need to.
Hold on. Let me take a
Yeah.
we forgot this line. Sorry.
Yeah.
We that one in the result of push.
Just gonna have a nice big array.
That one. I just do this. I don't know, like, yeah, cause we need to check. We need to check.
If you hit a leaf node.
Yeah, if it's a leaf node or not. Then if it's not a leaf node, we're gonna push the new current sum. If leaf node, then we're just gonna return, right?
Yeah, otherwise you would have an infinite loop if you don't have a base case.
Yes, this is the base case, line 54, right?
Yep.
Okay, so should we run it?
Wait. Last question. So we want to return results, right? But we don't need to put them in this bracket, right? It's extra bracket. We don't need that bracket, right? We just put it outside the bracket.
No, inside. Yeah.
Inside?
Yeah.
Yeah.
That is Ray taught me.
Wait.
Yeah, well, you can't duplicate.
Yeah.
Because it's complaining, so I was not sure. Okay.
Yeah. So.
I hope you all wrote it right.
Yeah. So I'm gonna run it. Then we're gonna discuss time complexity and space complexity. So what we gonna do?
Well, you can't run it in VS Code because you don't have, well, you have to have the input.
Yeah.
You have to have your test cases or test input.
Which we didn't create. We're too lazy.
Yeah.
It's so annoying to create a test.
I know. For trees, it's very difficult.
I gotta create all the trees and then
A lot of work.
all the mocha chai tests.
Right.
Aw.
Look, my solution is right for this one. Same thing. Look.
No, go back. Go to the other one. Go to the other non-working solution.
Well, there's something missing
That
somewhere.
is not my problem. Doris has typo.
Wait a minute.
No, I see
Remember, you're the navigator.
the We shouldn't put
We never call the
result
function.
in the
We never call the
Where?
function.
We called.
We call the function.
No.
So in your 17 and 18, I can see in your solution, you didn't put return result in another bracket.
It's supposed to be. You declared a new function and then told it to return something.
So what's the problem with the extra bracket?
Because you're defining a. You're basically. Are you even redeclaring a function? I don't know what that actually does in JavaScript. That's like a weird part. I don't know what that does.
It doesn't really matter, right? The bracket.
No, it does. It does. It for sure does.
Wait, I'm missing. What's missing?
Because.
So what's the difference between?
Oh yeah. You need a bracket. You're returning something. Because unless you're using
But no,
arrow
the
notation, then you could.
The calculate
can
branch
get rid of
sum
that.
is declared outside of the function, so I don't know why there's brackets around
want
the
to
calculate
return
branch sum.
I feel like the return result should be outside of the calculation branch sum.
There should be no brackets around with the calculate branch sum. The return should not be wrapped.
Because the purpose of the recursion function is put all the branch sum into this result array. So once the recursion function is done, that means we already have everything in this result array. So
Yes.
Okay, should I do that one then?
Why are the brackets there?
What do you? No. What is return? Return from what?
Yeah, then we don't need a bracket. I don't think so.
I don't think that's gonna run.
Let me see.
That's
I
not
think
gonna
the
run.
bracket.
That's not gonna run.
Good job.
What the heck? Okay, so what's wrong with the bracket?
Because you've already declared your function. It's like a redeclaration or something. I don't know what it does. It's a weird part, but you already declared it once. So with the brackets, you're like declaring it again.
So this is like a call. This is like a call 17. Then you return outside, not to return inside the new function if you put the brackets, right?
Yeah.
Okay.
Yeah, because calculate branch sum is the help function. It's calling there. It's returning something there, or it's manipulating your sum total.
I wish I could have read the error, but I don't know because I don't know what it does off my top of my head. But yeah, that's
okay. I can show you the error if you like the error.
I just want to see the error, like what the actual error says.
Many errors.
Unexpected token. Okay, simple.
Yeah. Let's remove brackets.
It just has no idea what you're talking about. Okay.
No, you say line 17. Remove brackets.
Yeah. That's what the error is. I didn't know if it was gonna be something fancier than that, but that works.
What the heck is like?
Yeah. Oh, you still have an extra bracket.
Yeah.
Oh, then. Okay, pretty good.
Pew, 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 pew. I'm gonna get a soundboard.
Yeah.
Okay.
Oh yeah. So Kazi gave you a list of equipment to get, right?
Oh yeah, I gotta get a stream deck now.
Oh my goodness, sounds like a lot of stuff you got to get in. Or
okay, David, you're gonna write a time complexity and a space complexity.
I'm gonna write it. And do I explain it too?
Yes, because the audience wanna see you explain, not me.
You did great. I don't see the issue.
Respect your audience.
Jen, you can practice, Jen. Come on.
At least this. I got my power system. Everybody can do the.
You understand the time complexity now?
Red plus black equals navy blue. Then all the navy blue plus the green equals purple. Okay, so.
Time complexity. Come on, Jennifer. You want to give it a crack?
Time complexity. So it is input is every n. Okay, I'm gonna look at my notes. Because we go through every node in the binary tree, or every node in every branch, and adding that node's value to a sum. That's why it is time on.
Yeah, that's basically it. It's
pretty good.
it's linear time because you literally have to traverse every single node in this tree.
Mm-hmm. And only one time.
Yeah, one time.
Okay.
Linear time only traverse one time, right?
Yeah, for each node.
This is like a Friday method. Okay, so space complexity. Okay, it's a little complicated. Okay, I'm just gonna read it. Okay, space complexity a little bit tricky here. We go through every node. We have the sum, and we add that sum. Okay, to an array. Okay, I don't know, like something OS comes out.
Oh, what?
What's that?
S?
Where S is the number of sums that we are storing in the sums array. You will be technically right, but we are also doing recursive call in the algorithm, and where recursion works, yes, that it adds calls to the call stack that accounts for extra space, and that space is more than the number of sums that we have, because every call we make to the call stack signifies a node in the binary tree, and these more nodes in the binary tree, then there would ever be sums. So if you really wanna be technical, the space complexity is gonna be OS plus N. Oh, sorry, OS plus N. Okay, where S is the number of sums and N is a number of nodes. But in bigger O notation, we tend to take into account the largest value. Since where this grows, this is gonna be very, I don't know how to pronounce that one, but it's called the
asymptotic? It's not asymptotic.
Like you can ignore.
Oh, negligible. Gotcha, yeah.
Right. Yeah. Okay. That's why it's ON.
Right.
So the actual space complexity is gonna be ON. So that is I learned from Rain about cossack and come out with more technical explanation.
Right. So like I said, the recursion is the function. Anytime you have a function call, that's an actual call stack that gets allocated, a call stack or a stack frame within the call stack that gets allocated to execute that particular function. Every function has a memory space allocated to it. In the heap, it's referred, and then it gets put onto the call stack. So this previous call is calling another call, and you cannot, and if you're stacking it up one on top of the other until you get to the base, the final case, then you can start getting the values from the previous one, because it was dependent on the child, right? On the successive one, the previous stack. So that stack builds up until you get to your final base case. Once you get to the base case, it gives you that value to the previous sum, and then that one now knows what the sum is. It adds it to the previous call stack, and on until the first call you made. So that's your stack frame that keeps growing, and that's why you can run out of space if you have a lot of nodes. And that's why recursion is not always the more practical implementation. If they gave you a constraint of n goes from 0 to a million or 2 billion, whatever it is, then you have to know that you cannot use recursive solution. You have to use an iterative solution.
Yeah, Davian, can you type what he just said? Because I want to make a note.
Actually, what you read from your notes was exactly right, because it's also the call stack plus the tracking of your sum.
I know, but I don't want the people see me typing on YouTube.
What?
Yes, I always have typos.
Why can't you just copy and paste from your notes? Oh, you have a physical written note.
Like this.
Oh, okay.
Just watch the replay and put the closed captions on, and it'll be there.
Type Ray what the Ray just said. Are you gonna do that, Davian?
What am I gonna add to that? Okay.
I mean, or you can just say what you wrote, what you have on your notes, and then any one of us can type it out.
Yeah, that looks pretty. This explanation is good. I don't know what to add to it necessarily.
I got this one from Java Solution, but it's the same question.
I mean, I just added more specificity on the call stack, but what you
said
is exact.
Then the YouTube audience will get mad. Listen.
Who you?
They're gonna laugh seeing this.
Okay, I'm gonna read then you type Davian. Okay. And you can shorten it. Okay, so space complexity here a little bit tricky. We go through too fast.
Oh, I'm typing all of that.
He's typing.
Okay. All right, just go. Okay.
Okay, so we go through every node.
You're in secretary now. Okay.
we had the sum, and we adding the sum to the array or list. Here we have array. Then you put space Sorry, you put stuff. I don't know, but I see cracking the interview has that one too. But I do not have time to detail log that. So you just put this. Okay, then you can type. Okay, where S is the number of sounds.
Okay. Oh my goodness.
Okay, that way, yeah, not end yet.
What? Now what? Look.
She didn't say period.
Yeah. Okay, where S is that we are storing in the sounds array.
What? You write that. I don't know what she said.
Where S is the number of sounds that
That
we are storing in the sounds array.
That we are storing in the sums array. Yep.
Yeah, actually it's the result, but it's same thing. Yeah. Okay. You will be technically right. Okay. But we are also doing recursive calls in the algorithm. And where recursion works, yes, that it adds calls to the call stack, comma.
Yo, this is getting exhausting. Someone else has to type.
No, you type. Almost done. That accounts for extra space.
I love for
Repeat
Debian.
that.
Only Debian can do it.
Put an F in the comments. Next week we're going live.
Accounts for extra space.
Okay.
Hold on. What are you?
I don't know.
Okay.
I don't know.
Okay, we will technically be right, and then we're also doing recursive calls in the algorithm. Yeah. Where recursion works is that it adds to the call stack. Adds calls to the call stack.
I think I'm writing that correctly.
Yeah. That accounts for extra space, comma, and that space is more than the number of sounds that we have. Okay, we have, because every call we make to the call stack signifies a node. Wow, you can understand my signifies. I don't even understand myself. You are genius, Davian. A node, okay. Oh, sorry, in the binary tree. Not finished. A node in the binary tree. And there are more nodes in the binary tree than there would ever be sounds.
Oh, you be starting to stop at weird places. Okay, in the binary tree, and there are what?
Huh? In
More
the
nodes than sums.
There would ever be sounds. So if you really wanna be technical, what are you laughing? Look, you keep on laughing, then I'm gonna make a mistake. So, if you really wanna be technical, the space complexity is gonna be OS plus N. You know the one I wrote here. OS plus N. Plus N. Yes. Where S is the number of sounds. And the N is a number of nodes. Okay. Period. Then, but in bigger O notation, we tend to take into account the largest value, since when this grows, this is gonna be very this negligible, whatever.
Negligible.
Yeah, negligible.
Negligible. Negligible. What? Negligible.
Okay, last sentence. So the extra space complexity is gonna be ON.
Oh, I see.
Not extra. Extra.
The expert? I don't know what you.
No. Extra. Okay, fine.
Okay.
It's gonna be ON. Okay, good.
I
Like,
think this is
Ryan, do you have any to explain
Yeah,
or help us
sure.
understand? Yeah.
So technically, what they're saying is that you have to account for the separate sum that you're keeping track of, right? You have an accumulator, this array, that's keeping track of a sum every time you visit each level or each node. So that's space, you're tracking that, right? The sum at each node. You're accumulating the previous node's values. So you have that sum, you have that space taking track of the sum value of all the nodes you had previously visited. Plus, like I said, in recursion, each function call requires its own execution context, which is an extra stack frame in the call stack that gets pushed onto the call stack. So when you say, call stacks or arrays, you say push, it gets on, and you pop it off when it's finished. That's the technical way to say it for adding and removing elements or stack frames from a stack. So that O of n represents the number of nodes, whereas the S, the extra space, represents the array that you're tracking for the sum. But there are the sums can never be greater than the number of nodes you have, right? You can never add more numbers than there are nodes exist. So if you only had three nodes, you could only add two times, right? The first one plus the second plus the third. So that's only 2 times, right? It's always going to be one less, and no more than the number of nodes. So your sum can never exceed the number of nodes. So in time complexity, you only care about the fastest growing element or variable in your equation, right? So time complexity, you ignore anything that is over a large data set. You discard anything that doesn't grow as fast as your largest moving factor, and your largest factor is n, because it's like we said, the nodes will exceed the number of sums. So you discard the sums and you're left with O of n.
Yeah.
Right. So you always do that. You always remove the constants or negligible factors in your time complexity or your equation. Same with space.
Right. Okay, I don't understand on Friday, you say iterative is better than recursive. Then today is recursive better than iterative.
Right. So we implemented it recursive because you were calling the function over and over again until you hit the base case, right?
Yeah.
So that recursion, like I said, is calling a function. A function requires memory, an actual execution context in the JavaScript engine, right? It's actually allocating some memory, physical memory, for this function to be called. In the function, you have a simple addition, but your function could be much more complex than that. But whatever, this is a very simple function. You're just adding 2 numbers, but that actually takes up memory. Memory allocation is required for each function calls, and you're calling the function over and over again. At most, you're calling it, 4 times. Or, if you have 4 levels, or 3 times, whatever, n minus 1. So that's just the what space is required when you're using a function call, which is the recursive call, because recursion, like I said, is functions, right? Functions require memory. So whereas the iterative, iterative solution would just be what we did on Friday. You would just use a while loop, and you would just do a while, and until you hit a leaf node. There are no more nodes or children, right? So if you did it iteratively, you're not calling well, I guess you would just each time you traverse through the node, you're just keeping track of the sum. You're not calling another function again. You're within the same function, right? You're not calling another function again. You're just adding a number, the previous value. So you're not, so you say, okay, go to your left, and the left node, which is the child node, until you hit a leaf node, and that's it. So that you still have to traverse. The time complexity will be the same because you have to traverse to each node to get the sum total, right, of each path or each branch. But in terms of space, you're not calling a function for each one. So you're only keeping track of the sum. So that would be constant time. So that's the difference in iterative implementation versus recursive. But so the takeaway for the most part is you have to understand what is really most important for most teams or the product owners. Is it your space or is it time? Which is usually the more important for most use cases in practicality? Do you care more about your space or you care more about your time?
Oh, so it depends on different scenario, right?
Yeah. But of course, there's a caveat with a recursive call. You have to be careful about space because you have a stack overflow, right? If you allocate too much space to too many call stacks, you can run out, and that's why you have a stack overflow, and you run out of memory.
Yeah.
But aside from that, I mean, generally, most people or most teams or project owners or wherever who's running this, setting the requirements, care about the performance over time. And and why is that?
I mean, bigger company has more memory, right?
It's not, so it's more about they want performance.
They care about time.
They care about performance more than the space. Space is you can
buy more space.
RAM is cheap. Yeah, you can just buy more memory. So if you look at the cost benefit or of how much it costs to purchase more RAM or hard drive space versus processing power. Processing power is CPU. CPU is usually a lot more expensive than memory, RAM, or hard drive space. So in terms of cost perspective, usually CPU costs much more relative to your memory. So space, time is usually cheaper in the end, performance. Plus, no one wants to wait that long, right, for your system, whatever your thing is that you're waiting for.
That arguably costs more.
Yeah, I mean, people drop off when they visit the page, right? They don't want to wait.
Yeah, different purpose.
Yeah.
So you weigh different according to use case.
Yeah.
Yeah. But yes, the Friday recursion is the space complexity is log n, right? From Friday.
Yeah.
Okay.
Yeah.
Yes.
Because you were splitting the difference, you were only evaluating half the tree or subtree at a time. You didn't have to do the other half. You said, okay, am I greater or less than this parent node?
Yeah.
Then once you picked the direction, left or right, you didn't have to calculate that. You discarded half your possible solutions. So you're saving time.
But it's like a binary search tree, so.
Yeah.
Yeah. You're gonna eliminate the left.
Yeah, but this is not what we're doing. We did something else. You had to go through you had to traverse through each node to get the sum, right? This is a different use case.
Yeah, different use case. Okay, now I understand better. Yeah. So you cannot memorize, say, binary.
You can't split the difference because you're not going to find the sum of the other branch that you didn't visit. You were forced to visit every node.
Yes, understand. I not with your guys' help and explanation, I understand the better time complexity and space complexity.
Yeah, it takes time.
Yeah.
It's a new concept and it's far different from arrays. So. Or a normal object, table, hash, whatever we're calling it, dictionary. So, but you're drawing your charts better. No, you actually did well.
I can be graphic designer.
Yeah, you're gonna be the new technical architect because you have all the good graphs.
Color system.
Doors too. You guys need to look at all.
Yeah,
doors.
I can't wait till we get to
Crazy.
systems expert. You're gonna be just architecturing all over the place.
Hey, by the way, can we go back to my graph because we didn't talk about space complexity and time complexity on my two solutions.
Yeah.
Ooh, let's do
You
that.
can
I don't know if I want to see that.
Stop presenting. You can share your screen for that.
Yeah, thank you guys.
Yeah.
Because I'm really
I'm
curious.
gonna save that and drop in the chat. See.
Okay. Can you see my graph right now?
Yeah, that's gonna be very complicated for visual. So like
Well, we could take a track.
have different scenario.
Well, there was no use case. This was just an implementation of a binary search tree.
Okay. Oh, I need to, and our solution, I need to remove the bracket.
I removed it already.
Oh, thanks so much.
No problem.
Otherwise, it's error.
So for the solution one, I guess the time complexity log, but I don't know log what.
I mean, but you didn't solve a problem. All you did was implement a binary search tree. So you have to you can't be any better than O of n because you're building out every single node, right? You're just implementing, constructing.
Oh, so
right? I mean, this is not, you're not saying find me the shortest path or find me the closest something to this node. You're literally just building out every node. So
I know
you
that.
can't
Okay.
you can't go better than O of n. Oh, but it could be O of n squared, I guess, depending on how you do it.
Would you say, yeah, would you agree with n squared or
I don't
more?
know. What is the code again? I can't see it.
So the code is like this. So
Oh, you have recursion. Yeah.
we have recursion function, and in for loop, we would do everything from the beginning.
Yeah. Oh,
And
you have to start from the beginning.
In every loop, yeah. In every loop, we would go from 8, start from 8 and go down and go down and go down and
Yeah.
come back.
Up to
And
8 again.
return.
Oh, yeah.
Yeah.
Okay, if you're coming right back to the root, yes, it's O of n squared, at least. Yeah.
Okay.
Can I add something?
Yeah?
I feel like the for loop itself is the O of n, but then when you call the recursion, it should be a log n. Because when you do recursion, the recursion only run the half size of the tree because you
Oh, yeah.
So
Huh.
I don't know. It's kind of like,
Is that what's going on? Let's see. The recursion it's checking left or right?
yeah.
The recursion?
Like imagine if you have a value.
Yeah.
Yeah.
And you want to compare values. That means you face two choices. You only go left or right. So you only
Right.
take the half size of the tree.
Yep.
So together will be like a O of n of log n.
Yeah.
Sure.
Well, average case, I guess, but I guess worst case, what if you get a flat
Yeah.
tree?
That's
Tree.
That's worse.
A linked list.
A
Yeah.
linked list, exactly.
Yes, then it would be O of n squared.
Yeah.
So you're saying average time or the theta, or that's the best case scenario is it split in half. It would be n log n is your best case. But you always take big O is known for worst case. Big O is standardized on the worst case, not your average or your best case. That the theta of n is, I think, your best case or your average case, and there's another one, omega,
Yeah.
something like that.
I forget which one is
represents
which.
big O represents worst case. Yeah, theta represents, I can't remember if it's the worst case or average case. I mean, best case or average case, and the other one, if it's omega or whatever Greek alphabet it was, represents the other one.
Sorry. So did you guys just say that the recursion function itself is big O of log n and
Best case scenario, I think, sounds like O of n log n, but big
Yeah.
O is not best case; it's worst case. So it should be n squared is base if you had a flat tree or just a linked list skewed.
I guess.
oh, so still n squared.
Yeah.
I guess best case, absolute best case would maybe be O of n, but that sounds super rare if you're just keep pushing on top of the stack.
Oh yeah.
If it's like somehow already sorted.
Wait, isn't best case O of n be a linked list then, right? If you're just adding
For
along,
both,
yeah.
I guess both best and worst case is a linked list depending on which direction you're going.
Huh. I have to look into that.
unless you need a balanced tree, which is another thing.
Yeah, I mean, we could just make it something with 3 nodes or 4 nodes and make it all left, and I think that would be just O of n.
Yeah.
Yeah. That would be best case, O of n. So maybe it's n log n. I don't know. Now I'm confused.
I guess average case it makes more sense now. Just somewhere in the middle.
Or maybe just average over n log n and worst case n squared.
We can always Google what is the time complexity for building a BST, for implementing a BST.
I still need to find a use case in real life to actually implement a BST. I feel like any case that has it, there's already like a library for it that I just don't know.
Yeah. Well, yeah. When you just do in order BST, it literally is sorted. Everything's sorted.
Yeah.
So that's how the numbers fall. Like, it's just calling the use cases like, I don't know, the value of the nodes could represent distance from some other whatever location, and it just happens that it could be in a BST fashion, or how you construct the locations, the places that you're mapping.
So is anyone doing any research, or this is our current current how to say result, current assumption?
Yeah, for now we could research it.
Okay.
Yeah.
We can come back if anyone had any new idea.
I'm definitely gonna research it next week.
Sorry?
I'm definitely gonna be researching all of
would
this.
have to be. Yeah.
I have a question. So, like Doris, those stuff is one legal question, or it's just general implementation for all the traverse?
Just this one. The
all graphs. Yes, for one question.
for one question, yeah. For this
My
question.
God, one question take that long to solve.
How many hours?
Yeah.
Is that like a hard question?
Probably not.
I would think that's like medium, or at worst.
Ew.
I mean, if you try to implement all the other methods, like inserting is one of the tougher ones. Search is search is.
Okay.
I don't know what the time complexity is for search.
Yeah, we will gradually see those, I guess, in future.
Yeah.
Definitely.
Any idea for space complexity?
I think it's. Well, at worst, I mean, at best, is O(n) for sure. Constant is a constant then, right? Or is it constant? No, as the input changes, your space grows if you're using a recursion. So it can't be any better than O of n. So your space grows as in the same fashion as your time complexity, I guess. Okay, I'm gonna have to look at that up too.
Okay. Okay. Look up later.
Yeah, I feel like it's open.
Yeah, I feel like too. Okay, the solution 2.
Another solution. Okay, how many more?
All of them.
Like,
Oh, this is the one we covered already.
All of them.
It was a very clever implementation.
Okay.
Yeah, we did it together.
Okay.
Okay.
Great.
So the code is here.
Is it more than one recursion?
I think this one is much shorter. It looks like big O of N. How do you guys think?
Wait a
Hi,
minute.
Beth. Beth,
Oh,
are you what? Coming for the
How
Maybe
are you
here.
guys?
good.
We're great.
We're wrapping up.
Yeah.
Wrapping
Are
up.
you?
Yeah.
I
Yeah.
think his summer you summarize.
We've been on for over 2 hours.
Yeah, we have.
We
Yeah.
started over 2
We
hours
actually
ago.
started on time too, so it was.
Yeah.
But you're welcome to join.
The good news is you're now on YouTube, kinda, and you can watch it there.
Yeah.
And I like your background, virtual background.
It's very pretty.
Is it like nighttime for you? No, it's afternoon.
Who knows what time it is? Yeah, it would be afternoon, I guess.
Oh, sorry, I was distracted.
Yeah, because he used nighttime virtual background. Fine. Ignore me, please. Continue. You're big old. Ignore me, please.
Although hide, no.
Okay, I can't pretend to understand. It's too advanced for me, that one. But I understand the sound of it.
What do you guys think? Does this make sense?
Can I say something?
Yes.
I feel like the solutions are very similar to the first one. The only difference is that we don't have the for loop. So that's why I feel like the time complexity maybe just the off-end. And for the space, whenever you use recursion, it's almost the same as time complexity. So it must be like a overband, I'm guessing.
Okay, makes sense.
You have answered, Doris?
If everyone agree with this, yeah.
Oh, okay. I thought you are testing us.
Yeah. So it's either. I think at worst it could be n log n, and at best O of n.
Oh.
It's just whether it's O of n or n log n.
Time or space?
I think both.
That's the way to go for binary trees or trees.
N log n, not log n.
Oh.
Yeah, definitely not log n because you have to put in every node, so you have to have at least n.
Like this?
Yeah.
Okay.
Yeah.
I'll look it up and maybe
Yeah.
let you guys know as well.
Hopefully we're on the right track.
Yeah. Ray, you are big old expert.
I know the basics. I can explain to you the basics, but
Big old
coming up with
expert and a recursion expert.
I'm scared that that's only the basics.
Hey, actually, I'm pretty curious about Elva's background.
Me?
Yeah, can you please introduce yourself, please?
It's a little bit embarrassing.
Huh?
No, not
Um,
why?
It's okay. I'll stop
I
recording.
went to boot camp like 3 years ago.
Yes, I did. Yeah. Oh yeah. The AlgoBus. Say it proud, Jen. You, you get a transit pass.